Welcome back, engineers. We are discussing common trade-offs in system design, and in this video let's look at an interesting one, which is storage versus computation. I hope you're ready. Let's get started. So whenever there is a user request, there are multiple ways to answer to this request or respond to this request. You can start computing what the request needs at runtime, at real time, or you can pre-compute it, put it somewhere and send it back to the user immediately. Or the third way is just fire and forget. Just take the request, let the user know that you've acknowledged it, and then let the user come back for additional checks and status updates, and when your data is ready, just present it to the user, right? So there are multiple ways to answer a user's request. In this video, let's look at a couple of stories. In one story, we're going to see that pre-computing and storing it somewhere and then giving it back to the user makes sense in that context. And in another situation, if you pre-compute it, it's going to have a negative impact, right? So let's see these couple of stories. So here's the first one. So let's say we are at a social networking application, right? So there is a user can be friends with other users can be friends with some other users. So the network keeps building. So it's a simple concept of nodes with edges if you're into databases, right? But the point is, each friend is actually using the app. Users are posting some updates. Other users are reading these updates. So every user has some kind of a news feed which they will access whenever they launch the application. They want to see what their friends are doing. They want to know the latest updates. They want to have real fresh data at all times. And that's how any newsfeed system works in general, right? So if you're dealing with a large scale for this, right? Let's say we're dealing with 1 million users or something like that, beyond 1 million users, and every user, let's say, is having an average of about 100 friends, and every friend, let's say, is averaging about 5 posts per day, right? So we're looking at a reasonable scale here, and the job of the system designer is how to build feed for 1 million users, right? So whenever I'm launching the app, I would like to see some feed, some posts, some pictures, some videos or whatever, right? So we need to somehow balance this so that every user gets optimal user experience. They're getting the latest data, relevant data, ranked data and all that. And they want to have all this information whenever they launch the application at super fast speeds. So let's apply our favorite framework called PrOACT to this kind of a problem statement, and let's see how our decision would be there, right? So our problem statement says build a feed system for a social network. So it may not be always a problem to solve. Sometimes it can be a new requirement, and for solving this new requirement you might be having multiple choices, and for these choices you need to make a decision, an informed decision, and you need to get a buy-in from different stakeholders. So in that case as well, you can apply PrOACT. In fact, you can apply PrOACT to any of the real life situations as well, right? Your day-to-day life decisions, how to buy a car, which mobile phone to choose and whatnot, right? So try to use this framework. It's a very handy framework. Okay, back to problem at hand. Build a feed system for a social network, right? And these are the objectives. We want less than 1 second load time. Yes, whenever user is launching the application, we want all the data readily available. Handle 1 million concurrent users, right? Let's say there are multiple users, highly active usage for this application, and we want all the users to have a really good experience. So always the data should be fresh and relevant, and of course minimize infra costs while maintaining performance, right? Performance should not be hampered, and we have to manage infra costs, right? So these are our 4 objectives. Now let's see the alternatives. So in order to achieve these objectives, there are different paths we can take. One path is on-demand computation, which is the pull method, which means that when the user is launching the application, the app will make a request to the server will start computing. Okay, this is user 1 has 10 friends. Let's go to each friend and check if there are any updates. If there are any updates, start compiling them into some kind of a list. And then once all the users are done, you sort them or you do some pre-processing so that it is relevantly presented to the mobile phone, and then the data is rendered to the user, right? So this is one way of doing it. The second way of doing it is doing a pre-computed storage. So whenever a post is made by any user, you know which of the friends are more likely to actually access this information eagerly, right? So you might want to pre-compute this. You already know how the list is going to be presented. You might have some sorting mechanism, you might have some relevance ranking and all that. So why not just pre-compute it up ahead for all the different users and then use the push mechanism to just whenever the request comes, just push that data to the mobile phone, right? So this is the second path that we can take. Third path is a hybrid, so which is in between these two. Compute some of the things and then some things like quick checks on different users at runtime, right? So hybrid approach, somewhere in between on demand and pre-computed, right? Not do the full computation every time, maybe have some caching involved or whatever, right? So that's the third alternative we can take, right? Now let's see the consequences for each of these alternatives. So our objectives are roughly translated into these columns or features, you might say, right? So we have response time, computation cost, storage cost, data freshness, and scalability. And let's see how each of the alternative performs. So for an on-demand computation, like computing the feed for every user on every request, we have high response time because we need to actually compute the whole thing. We have high computation cost because of this, low storage cost because we are not storing anything. Data freshness is really high. This is an advantage we are getting here because every time we are computing data at that point of time, which means we are always getting fresh data. There is absolutely no doubt about it. And scalability is low for this because the scale at which we are looking at, it may not be feasible to compute for all the million users on every request, on every pull, right? So that's why scalability is low. Now let's look at the second alternative, which is pre-computed. So for this, our response time is low because we have already calculated whatever needs to be done and it is ready to be presented. Computation cost is also low because we are doing some kind of a background processing. We're not doing any real-time stuff. So we can pre-compute it, do it in batches, and we can do all sorts of optimization here. So computation cost is low, storage cost is a bit high because we are storing relevant information for many different users into the storage so that it can be accessed easily. Data freshness is medium. It may not have the freshest of data, but there are ways around it to keep it a little fresh. But scalability is really high, right? So with this, we can accommodate many users. And the last alternative is hybrid. So for this, as you might expect, it is somewhere in between on-demand and pre-computed. So response time is medium, computation cost is medium, storage cost is medium, and data freshness is high because we are still computing for some amount to keep the data fresh. Although some of it is pre-computed, we are still checking for any relevant new posts. So data freshness is high, and we can achieve some scalability with this as well, right? So these are the consequences. Now let's see the trade-offs. So for trade-offs, we mean that we are analyzing what are the things that we are gaining against which the things that we are losing, right? So for the first alternative, which is on demand, we are getting these benefits: low storage costs and fresh data always. And the things that we are losing are, it is a costly computation, relatively slower because we have to compute each time, and there is no scalability. And the next alternative is pre-computed. For this, we are getting really fast response times, cheap compute, scales really well, but the disadvantage is that we are incurring storage costs and data may not be the freshest that is available. And the last alternative is hybrid, which is the best of both worlds. So it is a little faster when compared to the pre-computed one because some of it is pre-computed, and it is optimized for cost in terms of storage and compute, and data is fresh, right? So it is a mix of both worlds. So it is not the super best response time that we can give to the user, but it is also not the most expensive one, right? So with this, we have all the data in front of us. Now it is time to make a decision. So take a pause here and think about it. What might be the best solution in this case, right? Okay, so I hope you got the answer. So we are definitely going with the option number 2, which is pre-compute, although we can do some optimizations. So with pre-compute, we can actually compute for active users. We can keep track of daily active users and pre-compute for these users. And for the rest of them, we can do incremental updates periodically as new posts come in. So we can do some optimization with pre-computation, but we want to give the best experience to all the users whenever they are launching. So we are not going to compromise on response time and user experience, and we're going to incur a little cost for doing this pre-computation and storage, and that is okay in this context because we want to prioritize user experience and response times in this case, right? So in this context, pre-computation makes sense. Now let's look at another story where if you pre-compute, it might have a negative impact, right? So we are at a completely different situation here. We are at a company called Awesome Credit Card Company. Let's say it's a very successful company. Many users are using this credit card, and the company has a lot of transactions happening per day, and they have a lot of data. And with all this, it's possible that there can be fraud involved. Maybe the percentage is low, but as a credit card company, it becomes responsible for keeping track of these frauds. It is a responsibility of the company to prevent frauds wherever possible. We have all kinds of technologies these days. We have machine learning, we have AI, we can do lots of data crunching, we can identify patterns, we can identify and analyze user behavior, we can analyze off the chart purchases, we can raise flags, we can put teams that are necessarily involved for keeping track of all these fraudulent transactions to prevent these frauds, to notify the user whenever there is a fraud, to keep track of all this, right? So let's say we are at such a company, and this is me on my phone. I got a call from the risk officer from this credit card company, and the officer says we detected a fraud transaction on your card, and I was completely unaware of this. I'm saying I didn't really do anything, but my card has been charged, and now I have to deal with all the consequences of this fraudulent transaction, right? So it's a good thing that they have actually tracked the fraudulent transaction, and then they have notified me, and I've confirmed to them that this is not my transaction, I didn't do it, it's a fraud one, just take care of it and all that. But how do the system actually do this? How does it work? And what are the steps that we need to do to make it a really accurate system, right? Because we don't want too many false positives, right? We want to have good accuracy whenever we are detecting fraud. So as a system designer, is talking to the devs here, and the system designer is saying let's build an accurate fraud detector, right? So that's the requirement that has been given to us, and let's see how we can do this. So as always, we're going to apply PrOACT. Let's see how this goes. So build a fraud detector for payment processing, and we are dealing with millions of transactions per day, right? Lots of users, lots of transactions, which means a lot of data incoming every day. So how do we do this? So we employ machine learning, obviously. So we're going to give machine learning models different patterns. We're going to build feature sets, have really large dimensional data, and then analyze user spending patterns, give device data, location data, any other patterns that are available with us. So we're going to build models with all this, with the existing data, and we're going to give in new data for every transaction to check against the previous metrics, and if there is any type of fraudulent behavior, it's going to flag it and raise it to us, right? That is a typical implementation of any prediction system with machine learning, right? Let's see the objectives for this. Detect fraud with high accuracy. Of course, we want this number to be high. We want the accuracy to be high, which means that we're going to have low false positives. So if you know a bit of machine learning, there's this concept called confusion matrix, which will give out all these numbers, how accurate it is and all that. So we want high accuracy, which means we want low false positives. And we also want analysis time to be less than 3 seconds. We want it to adapt to new fraud patterns. This is a very important objective, because once a model has been trained, let's say the model has been trained 2 years ago, and the same model is being used for checking against new transactions. It is possible that the fraudsters have actually learned these patterns themselves. They know when the system will detect it as a fraud and when it won't, and they've learned from it. They've adapted their methods. They've been learning new skills to cheat people, to scam people, and then do these fraudulent transactions. So we need to feed these new patterns into the system regularly and keep the model up to date, trained it up to date, right? So it needs to adapt to new fraud patterns, and of course we have to optimize infra cost, right? So these are my objectives as a system designer. Now let's see the alternatives. So here are the alternatives. First alternative is pre-compute risk scores for known patterns. So we have a lot of data at this point of time. We know what the patterns are going to be, and for each type of pattern, let's say we have assigned a risk score. So let's say a transaction is coming in. I know the features of this transaction. It's the amount, it's the date, it's the location, it's the category of payment, it's the category of merchant and all that. We can see all this and assign a risk score. Maybe it's a common grocery store purchase, you will have a low risk score. and if it is something somebody has purchased from the black market or something, you'll have a higher risk score for that, right? So you can actually pre-compute these risk scores if you have the patterns already with you. So that is one alternative. Second alternative is on-demand computation each time, which means that for every incoming transaction, we're going to calculate the risk score, and with this new computation, you're going to check for all these new fraud patterns. We're going to check for old patterns, new patterns, and we're going to give out a new analysis, new risk score. So this is on-demand computation. And the third one is the hybrid one, which is the best of both worlds. Pre-compute for some features, compute for others, right? So these analyses take a bit of time because of the multi-dimensional feature set, and sometimes it can take time, but we want to have analysis time less than 3 seconds. So for some features, we might do some pre-computation, which are not so critical, and for the others, we might want to compute the other features in real time, right? So these are my 3 alternatives. Now let's see the consequences. So as always, our objectives have been translated into these columns. We want to have accuracy as a metric. We want to have response time. We want to have storage cost. We want to have adaptability, and we also want to have scalability as a feature, right? Now let's see for each of these alternatives. First up, pre-computed, we have low accuracy, because whenever you are pre-computing with existing scores, we are missing out on new patterns. Maybe this new transaction has a different pattern, so accuracy is low, which means there can be false positives. And the response time is low. This is a good thing because of the pre-computation, we can get low response time, faster response time. Storage cost is high, we are pre-computing stuff, so storage cost is there. Adaptability is low, we are not able to see new patterns with this approach. Scalability is high because we have pre-computed stuff. On demand, we have really high accuracy. Response time is medium because we're going to calculate the whole thing freshly. Low storage cost, we don't need to store anything here. High adaptability, we're going to learn new patterns in this. Scalability is medium if there are millions of transactions every day, so calculating everything each time is a bit of a challenge, right? For hybrid, things would be in the middle. Accuracy will be high because we're going to pre-compute some stuff, and the rest of them would be computed on the fly. We have response time medium because there is some computation involved. Storage cost is medium, not as high as a pre-computed one, not as low as the on-demand one. Adaptability is high, we're still learning new patterns, which is a good thing. And scalability is also high because we have little storage cost and little computation, so we can achieve some scalability in this case. Now let's see the trade-offs. So for the pre-computed one, we have fast and scalable as the benefits that we are getting, and the things that we are losing are more false positive, which means low accuracy, and storage costs are added, right? On demand is the second alternative. We have less false positives, no storage costs, new patterns are realized, scalable architecture, and we have slowness in the response time because of all the on-demand computation each time for each transaction. And the third one is a hybrid one, less false positives, new patterns analyzed and scalable, but storage costs are added a little bit slower because of the hybrid computation, right? So at this point we have everything in place. What would be your decision? Just think about it, pause the video here, and we'll see the decision. Okay, so we have the decision here. We're going to go for accuracy and adaptability as a higher priority, and we're going to go with on demand for our users because we are such a big company, we don't want any transaction to be left out. So we might go for hybrid as well if response time is not so critical. So I've chosen to give more priority to response time as well, along with fraud detection and adaptability to new patterns. So if analysis time is allowed up to 10 seconds or 15 seconds, let's say, we can go for the hybrid model as well, and that can save us some costs, right? So it's up to you. At this point, I've gone ahead with on-demand computing because that gives us the best user experience, right? So two worlds, one world where pre-computation makes sense, another world where pre-computation does not make sense. If you have pre-computed the risk scores, we are losing out on accuracy, and that is not what we need as a credit card company, right? Like always in any system design, there are no right answers. It is what is applicable to that context and what the problem you're actually trying to solve, right? So with that in mind, I'll leave it as it is for this video. In the next video, we'll look at another trade-off. Thank you so much for watching. Please leave a like if you found this helpful. Please subscribe if you haven't done already. Thank you so much for watching. I'll see you in the next one. Cheers.